terms. The name of is that the SUV. This is very important for the physicians. Yeah. For example, at first I define the SUV. This is the standard uptake value. SUV. It's very important for physician. What is the formula? This is the SUV. Activity of each organs, yeah, divided to injected dose. I know how much injected dose to the patient, yeah. At the first, for example, if my weight of, and again I know the body of weight of the patient, yeah. At the first, I determine the weight of the patient, and I know how much activity I want to inject the patient. Both of them I know. Okay? I know. And after I take the image in the PET, okay? These computers have the ability to tell me the activity of the organs. If I contour my organs, segment my organs, my computer say that how much activity these organs. And if I know the activity of each organs from the computer after I imaging the PET, okay? And before that I know how much injected dose and the body weight. By this formula, I can calculate the SUV. The SUV say about the standard uptake value. Okay. How I can interpret? If, see here, this is important. The SUV is approximately 2.5, taken as a cutoff between malignant and non-malignant pathology. Imagine I have the solid keystone tumor, I don't know. Yeah? I take the PET imaging from this patient. And I don't know this is a tumor or kyst. Both of them have the more metabolism and take the more FDG, but I don't know pathology of the tumor or the solid organs here. I don't know. How I can differentiate between malignant and non-malignant or benign and malignant? How? By the value of SUV. If my SUV value more than 2.5, I know this is the malignant. If this is lower than, this is the non-malignant. This is the example of the quantitative image. This is very good. And today's more physician use this to know or distinguish between the malignant and benign. This is the reference. Yeah? And this is a formula of the calculating the SUV. Okay. Before I injected the radioactive source to the patient, how I can define the activity. Because this is important for me. I don't allow to more injected or lower injected to the patient. If I injected more radioactive source to the patient, my patient have a source and go to the public and emitted the gamma ray and destroy the safety. And if I injected the lower radioactive, and I can take the good quality of the image. And this is the reason I select the enough injected. How I know how much I want to inject the radioactive to the patient. We have the instrument is that name is that calibrator. This is the dosimeter that show how much in the real radioactive. For example, see here, this is a vial or syringe, yeah, and I insert my radioactivities here, but I don't know how much radioactivities here, how much based of the millicurie, yeah. I inserted these vials, this here or this here, yeah. This is my holder. I insert this holder in the dosimeter, and this is a digital, yeah, digital control panel. I can see here how much radioactive this syringe or the vial. And this time I know this is the more radioactive or lower.
Low radioactive.
And decide this is the good for this patient or not. This is a dose calibrator. What is the role of the dose calibrator?
To see the activity of the radiation.
Yes, this is the, know the amount of the
Radiation.
What injected the patient. This digital monitor, we have some points to select the different material. For example, if I want to define the amount of the FDG, I select FDG, and after that I can see the amount of FDG. Or if I want to work with the SPECT, I select under technician. And after, because this is calibrated for the technician. And my material or radionuclide, this is the technician. And this point I should define or select the technician. This is the work of the nurse. What is the advantage of the PET at the summarize?
High sensitivity, high quality,
Attenuation correction.
Yes. Why we have the super or spatial resolution?
Because of the number of things.
Pixelated detector,
Yes.
no collimator,
No collimator.
ring detector.
Ring
After that
detector.
we have higher sensitivity, higher spatial resolution, higher efficiency, and this is the advantage of the this here. This is the SPEC vs PET. In the PET we have ring detector.
Ring detector,
and
yes.
high vision.
Here we have the
But
two
in
heads.
the SPEC we have dual head, and my head is rotated around the patient. This is the SPEC PET imaging. We have the
Ring light.
gantry, but this is we have
Two heads.
gantry and again head. And another comparison between PET and SPECT. In the SPECT, we use the single radionuclide. Okay?
Is
But
coincidence.
in the PET, coincidence or two gamas. And radionuclide in the PET, in the SPECT, what is important? Thickness. But in the PET, fluor 18.
Fluor 18.
And energy of the
Gamma
technicians is lower than
Don't kev.
Okay.
511
the
kev.
spatial resolution in the SPECT. This is
It's
10
11,
of
12.
millimeter. But in the PET is
5 to
of
6.
6. We have the bigger spatial resolution. What is the means of the, when I said to you my instrument or PET, yeah, PET instrument, have the spatial resolution, the value of spatial resolution is 5 millimeters.
Can differentiate two objects between distance between two objects is 5 to 6.
Exactly. If I have two objects and distance between two objects is a 5 millimeter, my instruments can distinguish. But in the SPECT, the smallest differentiation between two objects is 10 millimeters. And I know my spatial resolution resolution in the specs is decreased from the. Then I said spatial resolution in the PET better than the specs. But the value of spatial resolution this is in the PET is lower than. This carefully to the number, the value of the spatial resolution or the meaning. When I said to better spatial resolution, my means is that the value of spatial resolution is lower. Sometimes we have the mistake for this. I said in the space we can use the space city. Why use the city? For the have the anatomical localization. In the PET again this is two. This is the mic detectors, and again we can combine with the CT scan to take the anatomical and functional imaging. This is around the application of the PET in the oncology. You can see here the cancer, because we have the more uptake, these points. Or in the brain, you can see this is red is the high activity point. This area we have the more metabolism and attract or absorb the more FDG. Or in the lung cancer, you can see again this is my vision. This is my CT scan image, and this is fused CT scan and see here in the CT scan, I just see the anatomy, but I don't know this here we have more metabolism. But if I combine or fuse the PET and CT, I can see this here we have more metabolism, and I know we have this here we have, for example, maybe we have the cancer, but in the CT scan I don't know. This is the this table said that how I can inject the radioactive to the patient based off the scans. For example, in the brain scan, if I use a technetium, effective dose is that approximately 7 millisievert or 740 megabecquerel. This is don't use the need to then memorize. Just for the example, I know how much we injected the radioactive material in each of the scans. In each of the nuclear medicine part, we have some this table, and if some person that start early can use these tables to know how much injected to the patient. Okay. The theoretical of the nuclear medicine is finished, but at the follow, I want to show the some
commercial.
Yeah. This is
Philips.
one of the SPECT imaging and SPECT. Yeah, this is the from the Philips spec. And you don't need to memorize this the specifics. You don't. Just this is for the more information. And another instruments are for the GE. This is for the imaging of the heart. This is again for the imaging of heart. And the table is not straight. Yeah? Because this position, the patient have more flexible. Yeah? This position is like this here. This is the innovation of the Siemens for the cardiac imaging. And in Iran, we have the company to produce the SPECT and PET imaging in the Tehran University of Technology. This is one of the instrument. This is the PR SPECT. This is generated in the Tehran University for the cardiac imaging, and another PET or brain imaging, and this is another instrument we have. This is the PET imaging. I explain for this. The limitation of the functional imaging, what is? We don't have the anatomical information, yeah? For this, store this limitation, we combine the functional with the anatomical. You can see here, this is functional imaging, and this here, again, functional imaging, but this here, this is my CT for anatomical imaging, this is nuclear medicine for functional, and this is fusion of the CT and nuclear medicine. In the PET CT,
No. Yes.
in dual modality imaging, for example, PET CT, SPECT CT, yeah? This is my CT mode, CT gantry. You read about the physics, yeah? And this is my PET mode. Why we use the PET CT? This is reason why we use the CT combined with the PET imaging. One of the most important reason is for detection and localization. We use the CT combined with the PET image. Improve image quality and in the newer we have another instrument is PET MRI. This is very newer instrument in the nuclear medicine. Combine MRI with the nuclear medicine or PET. What is the difference between the CT and MRI?
CT uses radio.
Related to the image, quality of image. Difference between. This is here. In MRI, the soft tissues have the high contrast. Soft tissue. Yeah. In the MRI, the soft tissue have the more contrast. But in the CT scan, we have the more contrast in the bones, not the soft tissue. Yeah? This is one of the big advantage of the MRI to the CT scan. Related to this advantage, they combine PET and MRI until to receive the more soft
Better
tissue.
soft tissue contrast.
This is one of the instruments of the PET MRI.
Interrogated
And
PET
nowadays,
analysis
because
geometry.
artificial intelligence is the
Scintillation
PET MRI is
material.
very high-tech technology in the nuclear medicine. Okay. Do you like to see the movie from the difference between PET and SPECT?
Yeah.
Yes.
Yeah, sure.
Finish your Friday.
هذا يدوس واحد يدوس.
PET CT combines two different imaging technologies in a single scan: positron emission tomography, or PET for short, and computed tomography, or CT. Together, they result in a highly sensitive test that allows physiological changes to be precisely localized and evaluated at an early stage. PET measures the body's biological processes. CT generates high-resolution cross-sectional images of the body's anatomy. By combining both sets of information into a single, three-dimensional image, metabolic processes are mapped precisely and in all spatial dimensions. This helps to reveal the patient's condition at a very early stage. The combination of PET and CT gives a more accurate picture than the two scans performed separately, helping to facilitate a more accurate diagnosis. Physicians use PET-CT scans to aid in the detection of tumors and metastasis. Scans can also aid in distinguishing between malignant and benign changes at an early stage, determining the stage of a disease, developing a treatment strategy, and monitoring the response. PET-CT scans can also be used to evaluate Alzheimer's disease and heart disease. Metabolic activity is measured using so-called PET tracers. These are weakly radioactive biomolecules that behave like normal biomolecules and accumulate where needed. The PET scanner records an image of the tracer distribution as it collects in areas of higher metabolic activity, similar to cars gathering in a parking lot. These areas show up as bright spots on the PET scan. In principle, any biomolecule can be a tracer. Most often, however, radioactive labeled glucose is used, so-called 18F-FDG, which accumulates in tissues and organs with a high energy demand. Since the tracer decays quickly, it must be prepared anew before each examination. Before the PET-CT scan, the tracer is injected into a vein in the patient's arm. After that, the patient must rest for an hour to allow the substance to spread through their body. Then the examination takes place. CT uses X-rays and images multiple layers of the body in succession. The PET scan registers the decay of the tracer by means of the gamma rays emitted. A fused image is created from the dataset. (18F-FDG) glucose has a short half-life. After 2 hours, only half of the radioactivity remains. After 4 hours, only a quarter, and so on. The radiation dose from the two examinations corresponds, on average, to the annual natural background radiation to which every individual is exposed. At present, PET-CT scans are used to make mainly static images of the metabolic processes. The future will be dynamic imaging that captures and quantifies the metabolic processes over time. This will give physicians additional information to be able to diagnose, stage, treat, and monitor disease more effectively.
You have any question?
No.
No? Our class finished. And all of the files, the next day I transfer.
Okay.